Now, we are going back to probability. Probability can be introduced through sets. Sets are equivalent to events, as I mentioned before. And before I talk about axioms of probability, let me introduce a probabilistic model uh, of systems with inputs and outputs. Every time we perform physical experiments, we have trials as input and outcomes as outputs. The universal set is a nice example uh, of the sample space. And in the sample space, the events are defined qualitatively because the events are some kind of happenings, maybe an incident or an affair or a case. Sometimes it is an accident, and these events can be numerically represented by the sets quantitatively. And the sample space can be represented either the discrete or the continuous sample spaces. And in the discrete sample space, uh, we are dealing with integer type or discrete type symbols for the events or sets, elements in the events or sets. And in the continuous sample space, the elements are represented by uncountable elements. And we use probability in the mathematical model of experiments. Here we have two dice. We roll two dice, and the outcome of this experiment, we have two numbers on top of each die. Number 6 and 3 appear on top of two dice, and those numbers constitute okay. Continuing the probability concept, there are three axioms in the definition of probability: A1, A2, A3. These are called the fundamental axioms or uh, skeleton axioms. Number one axiom, A1, it says P. P is the probability function. A is an event A. So PA is greater than or equal to 0, saying probability of an event A is greater than or equal to 0 always. That means if you have an event occurring in A, then the numerical value of that probability function should be greater than or equal to 0. A2, PS is 1. By the way, the S is the universal set or the sample space. So the probability of the sample space is always equal to 1, which means the S can be regarded as the event of the whole universal set. So the probability of some event happening is always true. And A3, axiom number 3, P, big union, I start from 1 to n, A subscript I, is equal to summation, I start from 1 to n, probability P, A subscript I. If AI intersection AJ is the empty set for all I which is different from J. That is, for all mutually exclusive events AI and AJ between AI and AJ, if there are no overlapping elements, that means it's mutually exclusive concept. Then the axiom number 3 holds. That means the union of every mutually exclusive event, and that probability value should be just addition of each probability values of mutually exclusive events AI. Now let's talk about joint probability and conditional probability. The definition of joint probability, 결합 확률, is P set A intersection set B. If for two events A and B there is common elements in A intersection B, so that means if you take a look at the Venn diagram, we have set A and set B, and we have an overlapping region, and if there are elements within that region, then we say that there exists the P A intersection B. Okay, so theorem number 1, probability function P bracket A intersection B equals to PA plus PB minus PA union B. And theorem number 2, probability function P bracket A union B is the same as PA plus PB minus PA intersection B, which is less than or equal to PA plus PB. Here we have the equality. The condition holds if both A and B, those sets are mutually exclusive events. So that means A intersection B is the empty set. Then the equality holds for the theorem number 2. So what does that mean? We have union A union B, and the probability of that union A union B is numerically represented by probability A plus probability B minus probability of intersection between A and B. Why? Because the overlapping region, when you add probability A and probability B, and there are redundant number added because of that overlapping region, and that is the probability A intersection B. Okay, now talk about the definition of conditional probability, 조건 확률. Symbolically, we put probability P, the probability function P, bracket A bar B. Or we may say probability P, bracket A given B. Here A and B are events. For non-zero probability, PB, which is greater than 0, the conditional probability of an event A given B is described by this information. Probability P A given B is probability A intersection B over probability B. So we say this conditional probability is different from just probability PA, because we have condition B, and this condition uh, have effect on the result of conditional probability, which uh, usually, not always, but usually the value, the numerical value is growing, is increased, because uh, in the denominator part we have a probability of B, which is less than 1. So we have the reduced sample space S prime, which is just B, the event B. So the actually probability PA, with that probability PA, we have the sample space S, but for the conditional probability PA given B, the because of that condition, the sample space is reduced to a new sample space S prime, which is the same as B. Okay, so it is kind of a reduction in sample space S to S prime, which is B. So if you take a look at the Venn diagram, we have overlapping region A intersection B between set A and set B, or event A or an event B. We have intersection A intersection B, and that region is uh, uh, if you take a look at A side, then that's from that intersection region of intersection is from B. So it's uh, uh, for given B, that means our sample space, the sample space S is reduced to B. So you only take a look at the event B. The other events are gone. So on that B set B, you have the event occurring because of that event A. So that means that's just A intersection B. So on this reduced sample space B, you have the event A, which is just A intersection B. So here, uh, this is a very important concept. And let's say we have a theorem. If A and B are mutually exclusive, then we know that A intersection B is the empty set. Therefore, the probability P A given B is probability of the empty set over probability of B. PB is not zero. It shouldn't be zero. So, but P, the empty set, P phi is zero. So this is going to be zero. Okay, another theorem. If A and C are mutually exclusive, then probability bracket A union C given B is just addition of two probability, P A given B plus B C given B. Is quite obvious because we know the axiom number 3. So even though this is conditional probability, for mutually exclusive event A and C, uh, the union, the probability of that union is just summation of probability A given B and probability C given B. Now we can talk about total probability, PA. So here A is nothing but an event, any event A. And inside this event, we have a bunch of mutually exclusive events, BIs. Some of the BIs are included in A, but the other BIs maybe not included in A. It doesn't matter. Now, this total probability PA, 총 확률, I can say the probability of PA of any event A can be expressed in terms of n conditional probabilities of mutually exclusive events BIs whose union equals to the sample space S. So the sample space S is divided into mutually exclusive BIs. So we have conditions. BIs are all mutually exclusive events. They are not overlapping with each other. So BI intersection BJ is the empty set for all I which is not equal to J, or different to A, I, and J. Uh, intersection between those BI and BJ, uh, the the probability of that intersection value is 0. Okay, the second condition, the union of BIs constitute the sample space S. So the whole thing, we have n patches of BIs, which is not overlapping with each other. And that events, BIs, big union, I start from 1 to n, B subscript I equals to the sample space S. So we have a small pieces of BIs, and some of the BIs are included in the set A. And by doing this, the probability A can be represented by those small patches of BIs uh, 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 which are mutually exclusive events. So here is another Venn diagram representing A intersection BN or A intersection BI. Okay, continuing the total probability PA. So the any event A and the probability of that any event A can be represented by mutually exclusive BI events by using conditional probability of PA given BIs multiplied by probability BIs. So the total probability of event A is represented by this formula. PA equals to summation I start from 1 to n PA given BI multiplied by PBI. And this is the formula we use the axiom number 3, of course. Think of the union which becomes a summation symbol over there. So the proof is very simple. Let's start with the set A or event A. So A intersection the sample space S is the same as A, but the sample space S is represented by the condition number 2. The union, big union I starts from 1 to n, B subscript I. So A union bracket, big union I start from 1 to n, B subscript I. So because of the distributive law, 분배 법칙, the union symbol goes outside and intersection symbol goes inside, and we have A intersection BIs all together. So it becomes union, big union, I start from 1 to n, bracket A intersection BI. This is from the distributive law. Okay, let's take the probability function both sides. So PA is P big bracket big union I start from 1 to n bracket A intersection BI, which is because of the union because BIs are all mutually exclusive, A intersection BI, that patches of event A intersection BI are also mutually exclusive because of the BI. So big union becomes big summation over there. So, and it goes outside the probability function. So summation, I start from 1 to n, P, A intersection BI from the axiom number 3, because A intersection BIs are also mutually exclusive. And then it becomes summation, I start from 1 to n, PA given BI multiplied by PBI. So this is represented by this conditional probability. So uh, for any event A, the total probability of event A is represented by this formula, PA equals to summation, I starts from 1 to n, PA given BI multiplied by PBI. So this total probability of event A is represented by this conditional probability. Okay, let's talk about the Bayes theorem. The problem statement says how to find the inverse probability. So we already know, uh, we have already known this probability A given BI, where the BIs are the mutually exclusive patches of events constituting the sample space. But what is probability BI given A? So we switch the conditional events between A and BI. So from the inverse relation, we know uh, from the formula, probability P BI given A is probability A intersection BI over probability A if probability A is not zero. But the event A is always happening, so which is not zero, greater than zero from the axiom 1. Uh, so this is the inverse relation. And we also know probability A given BI is the probability A intersection BI over probability BI. And we know probability B subscript I is not zero. Because of that, the BIs are mutually exclusive patches of events. Here, uh, uh, we already know this conditional event probability A given BI. But we switch the conditional events. So this is called the inverse probability. So therefore, probability PBI given A is uh, probability A intersection BI over PA. Now we know the PA, which is the total probability. And from the formula, probability A intersection BI is probability A given BI multiplied by probability BI. So by using this conditional probability and the total probability, we know that. So from by the conditional probability, we have this formula here. So in the denominator, we have a total probability, and the numerator, we have the conditional probability formula. So therefore, probability BI given A is represented by probability A given BI multiplied by probability BI over the total probability, which is probability A given B1 multiplied by probability B1 plus etc. plus probability A given Bn multiplied by probability Bn. So the denominator part is nothing but the total probability.